Hello, in this video we look at projectile motion. We have an object that's going to be launched into space. It's going to follow a parabolic path, and it's our job to be able to model that path. At first we're going to start with the basic principles behind the scenes to figure out why we have the equations that we do. We have to rely on a little bit of physics. So your projectile is going to be launched, and our job is to find the parametric equations for the path, for the motion path. Alright, so let's assume that the projectile has a mass m. When it comes to gravity, that's going to be the only force that's acting on the projectile after it's launched. We're going to neglect air resistance. The force due to gravity is going to be minus mg in the j direction. And Newton's law, second law of motion, says that the force is equal to the mass times the acceleration. So these two forces have to be equal to each other, minus the mass times the acceleration constant in the j direction. It's supposed to be equal to the mass times the acceleration. And we can solve for the acceleration and get that it's minus g in the j direction. Alright, great. And from this we can get everything else. Last time we learned about integrating a vector function component-wise and getting the antiderivative. If it's acceleration that you're integrating, you get velocity. There's two components, so you do it component-wise. Integrating 0 is just going to give you a constant. Integrating negative g, who is a constant, gives you negative gt plus a constant. We're integrating with respect to time t. Just to distinguish the constants, we'll call them c1 and c2. This is your velocity vector. Well, let's do it again. When you integrate velocity, you'll get position. Now, we can use the initial velocity, though, to help us be able to figure out what's going on with the c1 and the c2. So we'll know the initial launch velocity, okay? And then that will help us to be able to find out what these constants are, C1 and C2. You can take a vector and break it apart. So you could, like we did in the previous video, we can have the constants written as a separate part here. And so we have the 0 minus GT and then C1, C2. You see, when time is equal to 0, that first vector zeroes out, and you'll just get the C1, C2. Okay, all right, great. The animation is a little out of order there, but that's okay. Now we're going to integrate velocity to get position. So we have C1 as the I component, minus GT plus C2 as the J component, and we're going to integrate each. So we get C1t plus a random constant minus gt squared over 2 plus c2t plus another constant. Using c3 and c4, we can break those apart, and now we have the part that is of t and then the constant part, because when we let t be equal to 0, we'll be at some initial position. Maybe we launch from the ground, maybe we launch from some distance off the ground, and so the initial position will be the c3, c4. That's not on this slide, but that's what it is. Okay. All right, great. So I call these first principles. This is basic calculus applied to vectors. Difference only is that I just call C1, C2 V sub 0. I call C3, C4 R sub 0. And so you can then have minus GT plus V0 minus 1/2 GT squared plus V0T plus R0. Is your position vector. And these are first principles. Just a rewrite of what's on this slide here. And so because of this, then what we can do is, depending on what information we're given, we can use it in a proper way to be able to figure out what the position function is. See, sometimes we'll be given theta, the launch angle. We'll be given the launch velocity, and then our job is then maybe we'll be lifted off some height off the ground when we launch, given these three inputs and the gravitational constant, we can figure out what the motion formula is. R of t is your position curve, your motion function. Okay. So if we know that initial launch angle theta, we can then take this v naught vector and find its I and j components. See, the cosine of theta is the j component over the mag of v naught. So mag of v naught cosine theta is the, j component. Oh, I'm sorry, sine theta, opposite over hypotenuse. Sorry, I was thinking of the the cosine is the I component and the sine is the j component. Sorry about that. And the v0 magnitude represents how long that vector is, but actually whenever you have the magnitude of a velocity vector, it's called the speed. So we have initial speed. So we can put that in there with v of t. So if a is equal to negative gj, as a v brace notation at 0 negative g, then v from above is the minus gtj plus this v naught vector. Component-wise, we can put them together and have mag v naught cosine theta as our I component, mag v naught sine theta minus gt as our j component. Okay, so instead of me just giving you the position function, we're kind of figuring out where it comes from scratch. It's great. Next, we should have minus 1/2 gt squared plus this v sub 0 times t. And now we have to figure out r sub 0. It's not horizontally left or right at time t equals 0. Let's hold it at the origin, but we go up. R naught. H. We go up h. That's what R naught is. Okay, so then have the part broken up. We have minus 1/2 gt squared on the j. We have v naught t, and then we have r0, the initial position. Broken up into three separate vectors like that, but we're going to put it all together in one vector. There's only one part that has a non-zero I component. It's the middle mag v naught cosine theta, and then the other three, the other component j has all three parts to it. You just did it. This will describe motion as you travel through space. If you know the ahead of time, the launch angle theta, the launch velocity, and the initial height off the ground. If you don't know that, then you wouldn't be using this formula. All right, great. So let's see an example. Classic example, you have a baseball and you hit it 3 feet above the ground. You hit it off at a certain speed, 100 feet per second. And then you got this launch angle. Somehow some computer was able to measure that it's the perfect 45-degree angle at launch. Our job, find the maximum height reached by the ball. And then answer second question, will it clear a fence that's 300 feet away and the fence is 10 feet tall? Okay. Hidden in this problem are all the things we need. We need the initial height h, 3 feet. We need the initial speed, mag v naught, who's 100. The launch angle theta, who's 45. And then notice that we're using feet. G can either be in feet per second squared or it could be in meters per second squared. So it's in feet per second squared. Okay. All right, great. So throw into our formula. We have R of t is equal to the I component, then there's the j component, but we know all these numbers. Let's plug them in. 100 times the cosine of 45 with a t on it. That's the I component. 3 plus that same 100 sine of 45t minus the 1/2 gt squared. And so, well, cosine of 45, sine of 45, they're both the same. They're root 2 over 2. And so we'll have 50 root 2 for those two parts. The maximum height occurs when the j component of velocity is 0. See, the j component is your tangent vector. I mean, the velocity is your tangent vector. And for you to reach that max height, it's going to happen at a time when the velocity vector is pointing directly horizontal. There is no j component to it. So take this j component, set it equal to 0, solve for the time to reach the maximum, and then plug that time into the plug that time into the original position function's j component. 3 plus 50 root 2t minus 16t squared. A little bit tricky there with the numbers without a calculator, but it does work out. You end up with 81 and an eighth. I think that is a 16th. 16th. An eighth. 81 and an eighth. So that's the maximum height reached by the ball. And then lastly, when the ball is 300 feet away horizontally, we can set the I component of position into to be equal to 300. Find the time it takes for the ball to travel 300 feet, and then we can plug that time into the j component of position to see how high off the ground it is. 3 rad 2 is the time. If we plug 3 rad 2 into the j component of position, we can plug that in and figure out that you end up being 15 feet above ground at that time t, when you have traveled a horizontal range of 300 feet. If the fence is 10 feet tall and you're 15 feet high, the ball is going to continue over the fence. Home run. All right. Thanks for watching. My name is Nakia Rimmer, helping you through this multivariable calculus journey. Please like and subscribe and comment down below and ask any questions. Don't be afraid. Reach out to me. I'll see you in the next video.